Section 3.5 is where we get to use Newton laws in different situations. Before we do, let's take a look at these three diagrams. In the first diagram, we have a mass that is tied to a rope and tied against a board. The object is not moving. In fact, for each of these cases, the net force is 0. My question to you is determine the tension in this rope, determine the tension in this rope, and finally determine the tension in the third rope. There should be one value for tension for each of these because it's one rope. If it's a rope, the tension is going to be uniform throughout it. So in the first example, how do I determine the tension in the rope? They tell us that the force of gravity acting on this object is 120 newtons, acting down. If the net force is 0, what must tension be on this object? And in what direction? So gravity is pulling down. In order for this to stay at rest, in order for the total of the forces to be 0, tension must be, the total must be 0, but tension must be acting upward and be equal to 120 newtons up. If you have 120 newtons up plus 120 newtons down, what's the total? 0. Okay. How about in this example here? Is there any difference between this diagram and this diagram?
Yes.
So in this, it's not attached or affixed to the wall from up ahead, but it's actually looped over a pulley. But let's isolate this block. If we were to look at a free body diagram of this block, gravity would be pulling down. And what's pulling it up?
Tension.
Tension. Has anything changed with our free body diagram? What would the tension be in order to make the total force 0? If it's 120 newtons down, in order to make this total 0, the tension must be 120 newtons up. Okay. I feel good about these two. The fact that it's tied against the wall is going to make the setup different, but the tension in the rope is still going to be 120 newtons. What about this last example? In this example, we have two masses, each contributing 120 newtons of gravity downward. What is the tension in the rope? I want to do a closed eye survey. Everyone close their eyes. Seal. Guy. Hands up if you think the tension is 240 newtons. Hands up if you think the tension is 360 newtons. Hands up if you think the tension is 120 newtons. Okay, open your eyes. Put your hand down, Tamala. We don't want anyone to know how you voted. There's no judgment here. Okay, in order to calculate the tension, we have to look at each individual object. So let's do a free body diagram of this first mass right here. Gravity's pulling down on it with 120 newtons. What must the tension be that's pulling up in order to make the net force 0?
40.
If it's 120 newtons down, let's look at this, we'll call it A, and we'll draw a free body diagram of A, showing only the forces that act on A. For diagram A, we have gravity acting down, 120 newtons. What is the only other force acting on this object? Jordan?
All the friction and tension.
Exactly. 120 newtons. On this mass here, gravity is 120 newtons down, and tension is 120 newtons up. What about for object B? Is it going to be any different? The free body diagram will be the same. The free body diagram will show that gravity is pulling down at 120 newtons and that the tension must be 120 newtons up. The tension of these two ropes is continuous because it's linked together and it's 120 newtons. Okay, taking a look at sample problem number 2. This is another classic example that you're going to have to be familiar with. This is an example where several objects are pulled together and attached by ropes and pulled by a rope. So we have a force of 120 newtons that is pulling on these three sleds. Sled 1 has a mass of 12 kilograms. 12.0 kilograms. Sled 2 has a mass of 11.0 kilograms. And sled 3 has a mass of 7 kilograms, 7.0. If you pull on these with a net force of 120 newtons, describe the motion of these sleds. What should happen to these objects? And keep in mind that there is no friction. What should happen if you apply a net force of 120 newtons? Based on Newton's second law, we know that this system should
move.
How?
How it's going to move in what regard?
So describe the motion. We have terms. Is it?
So it's going to be accelerating towards the east.
Perfect. It's going to accelerate, and it should accelerate in the direction of the net force. So let's calculate the acceleration of all of the sleds. In order to do so, let's make east positive. If I wanted to calculate the acceleration of these three sleds together, I would use my equation, net force equals ma. Rearranging this, we say acceleration equals net force over mass. Which is positive 120 newtons divided by all three of these masses combined. 12 kilograms plus 11 kilograms plus 7 kilograms. Punch this into your calculator and determine the acceleration of these three objects. Alex?
4.0 meters per second squared.
Direction?
East.
Good. 4.0 meters per second squared east. So the whole system is accelerating at 4.0 meters per second squared east. So this little sled, what's its acceleration going to be? 4.0 meters per second squared east. This middle sled, 4.0 meters per second squared east. And the big sled, 4.0 meters per second squared east. Since they are all attached by strings, they're all going to accelerate at the same rate. So we want to calculate the tension in rope A and the tension in rope B. In order to do these, we have to keep in mind that the acceleration is 4.0 meters per second squared east for all of these sleds. In order to determine this tension in rope A, let's look at the simplest possible free body diagram that we can draw, and that would be a free body diagram for sled number 3. Sled number 3 has a mass of 7 kilograms. What is the only force acting on sled 3? Take a look. What's pulling sled 3? It's this rope, and the force that comes from the rope shall be known as the force of tension, rope A. There's no friction, so nothing is opposing this motion. What we need to do is determine this tension. So how do we do this? Take 2 steps. Take the same 2 steps we've been taking for all of our questions in this chapter so far. First step, list all of the forces acting on this object and make sure you show the direction using a plus or a minus. So in this case, how many forces are acting on this object? 1, and it's the force of tension in the positive direction. Great.
There would be no gravity.
Well, there is gravity, but why are we ignoring it? Since this object is resting on a level surface, the normal force must be countering gravity. Okay? If the object is resting on a level surface, you can ignore gravity because it's not going to affect the motion. In this case, the motion will only be east or west. Second step in answering this question. That's a good question, by the way. The second step is to replace the term F net with the equation MA. So we're going to say, because this is sled 3, we're going to say M3A equals the force of tension A. So we have everything we need to solve for the tension in this rope. We have the mass of this object, and we have the acceleration of this object. So tension A is going to equal mass 3 is 7 kilograms, and the acceleration is 4.0 newtons per kilogram. It's positive because it's implying that it's going to the right. Tell me what the tension in rope A is. Okay, 2 sig digs times 2 sig digs. So our answer to 2 sig digs would just be 28 newtons east, or 2.8 times 10 to the power of 1. But you're not forced to use scientific notation, so there's no need to. So the tension is 28 newtons east. Okay. For part C, they want us to find the tension in rope B. For sled 2, let's take a look at sled 2 in order to determine this. Sled 2 is affected by the tension in rope B. It's pulling it to the right or to the east, and it's also being pulled back by the tension in rope A. So let's draw a free body diagram. Of sled 2 with a mass of 11 kilograms, showing tension in rope B pushing forward, and tension in rope A pushing backwards. So rope B is pulling sled number 2 forward, and rope A is kind of holding it back. Let's follow the same steps. The first step is to list all the forces acting on it, and the second step is going to be to replace the net force with the equation MA. So let's list all the forces acting on the object. What are the forces acting on this object, keeping in mind the direction? East is positive, west is negative. Who can list them for me? So let's start with the positive ones first. We have force of tension B minus, good, Do we see how we made the forward, our positive frame of reference, positive, and the backward, our negative frame of reference, negative? Okay, in the second step, we're going to replace it with the equation, so we get force of tension B minus force of tension A. Now all we want to do is solve for the force of tension B. So we have to get the force of tension B by itself. How do we get it by itself? All you have to do is take this and bring it over the equal sign. So we end up with force of tension B is equal to M2A plus force of tension A. When you bring FTA over the equal sign, it's going to become positive. Now let's sub and solve. Do we have enough information? Yes, we do. We have mass 2. It's 11 kilograms. We have the acceleration. It's positive 4.0 newtons per kilogram. And we have tension A. We calculated it just a while ago up here. It's 28 newtons. If you put this all together, what do you get for the force of tension B?
72 newtons east.
Close. 72 newtons east. Question number 3 from section 3.5 deals with an ice skater that is pushing against the boards on a frictionless ice surface with a force of 130.0 newtons west. If this guy is pushing against the boards with a force of 130 newtons west, in which direction is he going to move? If you push west against the boards, what direction should he move? Sandro? He should move east. Why is that the case? What's pushing the object? What's pushing this man? If he pushes against the boards west, what is the reaction force that is pushing him east? Not the normal. The normal is on the surface when an object rests on a surface. If you push against the boards with a force of 130 newtons west, then the reaction force is the boards pushing on you with a force of 130 newtons east. So if we were to draw a free body diagram of this ice skater, pushing against the boards, then the net force acting on this ice skater is going to be a force of 130 east. He pushes west to give himself some movement in the east direction. And he's pushing himself over a distance of 0.850 meters. Almost a meter, probably the length of his arms. And during that time, if there's a net force acting on this skater, then he should be accelerating. Let's determine the acceleration of the skater when he is pushing on the boards. In order to do so, let's take the same 2 steps that we've been doing. Number 1, list all of the forces acting on this object. How many forces are acting on this object? Look at our free body diagram. Let's make east positive. So the net force is going to be 130.0 newtons east. Second step, what should we do? What's the second step been? Alex?
What you do is now you decompose F net into MA.
Sure. Let's replace F net with ma. So we have the mass of the skater times his acceleration is equal to 130.0 newtons. Solve for A. A is equal to 130.0 newtons divided by a mass of 54.0 kilograms. What is the acceleration of the skater while he is accelerating? Or while he is pushing, rather? Punch in your calculator. .41 meters per second squared, or newtons per kilogram. And the positive sign implies that this is to the east. Good. When the skater stops pushing, the boards are going to stop pushing back. So if there's no friction on the ice and he's not pushing onto anything, what forces are going to be acting on the object?
Gravity and normal forces are going to be the exact same, so you can cancel them out.
So what's the net force going to be when he stops pushing?
0.
0. If he stops pushing, the boards are going to stop pushing back. Since there's no friction, there are no forces acting on this object. So is he going to be accelerating? The acceleration is 0. What's his motion going to be like? He just pushed off the boards. He releases. When the net force is 0, there are two possibilities for the object's motion. What is the possibility in this case? Good. He's moving with a constant velocity. The question tells us that he digs his skates into the ice and causes a net force of 38 newtons west. If he's traveling east, what will this net force of 38 newtons west do to the object? He's traveling east, the net force is 0. Describe the motion that this object is going to experience. So we have the skater who is traveling east . Applies this hockey stop, which gives him a net force in the west direction. .0 newtons. Let's determine what his acceleration is going to be. So you dig your skates in. The only force acting on the object is the force of friction. So the mass of the skater times the acceleration is equal to negative 38.0 newtons. Why did I say negative 38?
Because you let east be positive, so thus west has to be negative.
Good. So let's solve for the acceleration. The acceleration is negative 38.0 newtons divided by the mass of 54.0 kilograms. Let's punch this into our calculator and see what we get. What'd you get to 3 sig digs?
.701.
Negative 0.701. Do we concur?
Nope, I got 0.704 meters per second squared west.
Same?
Period 5 teachers, please excuse this interruption. One announcement at the end of the day. After-school tutoring is available for math in room 103 starting today. After-school tutoring for math is...
I wrote down that the acceleration is negative 0.704 meters per second squared east. Okay, the negative east can also be written as 0.704 meters per second squared west in the direction of the net force. The object always accelerates in the direction of the net force. Tomorrow, we're going to be taking a look at how far this individual traveled. Well, while pushing against the boards, the question tells us that the individual had a displacement of 0.850 meters east. So we need to calculate the distance traveled while he's coasting along the ice after he's pushed, and while he was stopping by digging his skates into the ice. So we're going to use kinematics and the acceleration from each of these stages to determine the distance traveled
For this lesson, an ounce